All right, so let's get back to the bunt case. Trying to figure out what the volume is. I guess, no, we said we didn't want to find the volume by fluid displacement. That would ruin it. So now we have a method for doing this. So let's review what the shell method was. If we rotate a vertical slice, which would be what in relation to the axis of rotation? Parallel to it, right? If I rotate that around, I'm going to get this little tiny cylindrical shell, which we thought would be a great way to slice this if your friends come over, just to weird them out. The volume of that little shell we can find and then add them all up from left to right. Now, the region that we're adding up from left to right is just this region here. So the area is usually the first thing that you're going to find if this were like a free response question. And that same region and same intervals of integration are what we're going to use. Now notice that there's a hole in a bunt cake, right? And remember when we had the perpendicular method, one accounted for holes and voids and the other one was for no holes or voids. The shell method, as you're going to see, doesn't really matter if there's going to be a void or not. Because we're slicing parallel to the axis of rotation, when we set up our radius, it's going to take into account the fact that there's a void, and we're not going to be slicing essentially where there is a void. So let's come up with the volume. I think we did this maybe at the end of class yesterday. But the shell method, which is for a slice that's parallel to the axis, or the pair-shell method, has how many pi's out front? Do you recall? 2 pi's. And it's pretty easy to remember 2 pi because the word pair in para-shell, para means 2, right? You can't just go to the store and buy 1 shoe. You have to get a pair of shoes, right? You can't just go to the store and get 1 pant. You have to get a pair of pants, which incidentally is just 1 pants, okay? Yeah, they're weird. And you can't go to the store and buy just 1 pre-made pie shell. Have you ever tried that? If you go to the freezer case and the pre-made pie shells are there, you have to buy them at least in pairs. You have to buy a pair of shells to make your pies. So that's another way to remember it. You can't just buy 1. So we got 2 pi out front. It's going to be the sum of the infinite slices from 0 to 3. That's from x equals 0 to x equals 3. Now we're going to have a radius, which I'm going to call r of x. And then we're going to have a height of our shell, h of x. And of course, the third dimension is dx. That's the shell method. 2 pi, the integral from a to b of the radius times the height times dx. Nothing is squared. So the question is, how are we going to come up with those 2 variable functions? Well, let's do h of x first, because I think that's the easier of the 2, or the more straightforward. The height of that slice is going to be the same as it was when we were finding the area of the region. It's the top curve minus the bottom curve, neither one of which is the axis of rotation, right? For the disk/washer method, since we were slicing it perpendicular, one of those was the axis. But in this case, it's not. So the top curve is just, what's the equation? 3x minus x squared. And the bottom curve is y equals 0. So let's go ahead and write that in there. I'm going to leave a little space. It's going to be 3x minus x squared. That's the top curve. Minus the bottom curve is 0. Now, of course, you don't have to put minus 0, but I always do for inventory purposes. Now the radius. That's the fun part. That's what makes this one a little bit different than the washer method. The radius is still going to be the distance off the axis. If you don't have an axis, you don't have a radius. So if your axis of revolution is at -1, let's draw a line from the axis to our representative slice right there. The question is, how far is it from the axis to any one of those vertical slices? Well, here's what I do know. I do know to get from x equals -1 back to the y-axis, I'm going to have to go every time 1 full unit, right? And then plus whatever the x value happens to be from 0 to 3, right? Okay, so remember, I'm slicing it from 0 to 3. So it looks like I'm going to go 1 unit plus whatever x is. So the radius should be what? 3x minus x squared. 3x minus x squared is 0. Now, of course, you don't have to put minus 0, but I always do for inventory purposes. Now the radius is still going to be the distance off the axis. If you don't have an axis, you don't have a radius. So if your axis of revolution is at -1, let's draw a line from the axis to any one of those vertical slices right there. The question is, how far is it from the axis to any one of those vertical slices? Well, here's what I do know. I do know to get from x equals -1 back to the y-axis, I'm going to have to go every time 1 full unit, right? And then plus whatever the x value happens to be from 0 to 3, right? Okay, so remember, I'm slicing it from 0 to 3. So it looks like I'm going to go 1 unit plus whatever x is. So the radius should be what? 1 plus x. Now let's see if that works, because remember, our x is going to vary from 0 to 3, right? That's what we're slicing from. So the smallest the radius is going to be is what? When you plug in your 0? 1, and that would be slicing it way over here at the origin. And then when x is 3, 3 plus 1 is 4, that's going to be slicing it 4 units away from -1, which would be over here at positive 3. And so in conjunction with the interval of integration, when you find the equation for your radius, you set it up so that you're never going to be slicing over the place where you have the hole. You're only slicing where you have cake. Nice. So there's your radius. It's 1 plus x. Now, in general, here's how we can remember it. It's always going to be right minus left if it's going to be a horizontal radius like it is in this case from left to right. The region itself, you can always let it be x. And the axis is to the left of the region, and it's at -1. So if I did right minus left, and I let x represent the region on the right, it would be x minus -1. And what is x minus -1? X plus 1, okay? Or 1 plus x. So you could do it that way as well. But drawing a picture, you can just reason through what it's going to equal. Now, when you get this far, you're going to get one check for your integrand and one check for your constant with your intervals of integration. And from here, really just evaluating it is the last step. And let's go ahead and do this one. The 2 pi is going to stay out there. What's the best way to find the antiderivative of this integrand? Expand it out? Yeah, I would think so. The derivative of 3x minus x squared is 3 minus 2x. But 3 minus 2x, unfortunately, is not a multiple of 1 plus 1x. If it were, I could do a real quick pattern recognition / U sub. All right, so let's just go ahead and expand it out. If I distribute the 1, I get a 3x minus x squared. And I distribute the x, and I get a plus 3x squared minus x cubed dx. All right, so 2 pi still standing fast right there. Combine like terms, maybe? Do we have any like terms? Yeah, we have a couple. I'm going to have a negative x cubed, and I'm going to have a 3 minus 1. That's a plus 2x squared, and then plus a 3x. Now, if I set this up right, I should end up with a positive number. So here we go for the antiderivative. It's going to be a negative 1/4 x to the 4th plus 2/3 x cubed plus 3/2 x squared. And I evaluate it from 0 to 3. So the 2 pi now hangs out front. Plug in the top. 3 to the 4th is 81. So you have negative 81/4. And then plus 3 cubed is 27. Divided by 3 is 9 times 2 is 18. Plus 3 squared is 9 times 3 is 27 halves. And then minus, what do I get when I plug in a 0? I get 0. Now that negative term in the front there kind of has me feeling a little bit nervous, huh? Because I know volume has to be positive. But 18 plus 27 halves, should that be greater than 81/4? Yeah, so it should end up being a positive number. I'm not going to go ahead and figure what it is from here. Let's go to the calculator. I think at this point, if you're okay with it, once we get the setup, we'll just evaluate it on the calculator. Because we know how to do it without a calculator, we can just focus on the new part, which is the setup. And just to satisfy our curiosity, maybe we'll go to the calculator. Plus also reinforcing good calculator etiquette. And the first step of good calculator etiquette for me is to validate the software license. There it is. It's validating. A non-pirated copy. Anyone watch the debate last night? 5 seconds of it? Was it good? A good 5 seconds? No, that's why it was only 5 seconds. Yeah. Okay, so since we've done all the work, let's go ahead and first of all just type in the value that we have. 2 pi, parentheses, negative 81/4, negative 81 divided by 4, plus 18, plus 27 halves. And this will give us our decimal approximation of what we got. 70.685. Okay, nice to know. So once you get the setup on a calculator problem, which is up here, this line right here, then you would just go straight to the calculator. That kind of obscures it. Let me get rid of that. So from the home screen, that's where we do all our calculations. To get the integral, we go math number 9, which, as we already said, is not a very good cheer. Kind of puts math a little bit artificially low. Math number 9. But you know what? Math number 9, it's a better cheer than the other way to get that, which would be alpha window 4. Alpha window 4. Okay. So let's go ahead and type it in. I've got a 0 to 3, and then my function that I typed in, parentheses 1 plus x, close it, and then open it, and then 3x minus x squared. Now notice, what did I not type in the front? 2 pi. I would say go ahead and put your 2 pi first. When you're staring at your paper, go 2 pi math 9. But if you forget it, just multiply by 2 pi on the back end, and that's what's nice about doing it from the home screen here. Now, if we set it up right and we evaluated it right, we should get the same answer, and there it is. Okay? Pretty sweet. All right, so there was your first taste of the shell method by way of the bundt cake. Unfortunately, we didn't get to taste the bundt cake. I bet it was good. Fewer calories, though. That's win-win. We're burning calories up here with our mind, and we're not consuming them. So we're lean, fit, mathematical machines. Mathletes. There you go. All right. Pair of shell. When your slices and your axis of rotation are what in relation to each other? Parallel to each other. Yeah. Okay. Example 9. Okay. By the way, all those words right there that I just skipped, let me just tell you what it says. Because we now have a way to find volumes when our slicing preference or method is both perpendicular and parallel, and those are the only ones you're going to be using, you can now decide, unless it specifically says otherwise to slice it a particular way, you can decide how you want to slice it based upon how many setups it's going to take or what your equations will allow. And then once you decide on the slicing method, you compare it to the axis of rotation. And if the axis ends up being perpendicular to how you want to slice it, then it's going to be a perpendicular perpenwashular. If the axis after the fact ends up being parallel to your independent preference of the slice, then you use the parashell. Does that make sense? So there's a method to accommodate your slicing preference. You don't really force the method anymore. Yes? An example. Oh, yeah, there was a follow-up. My bad. Thank you. Thank you. It said, what would happen if we rotated around x equals 4? Well, let's see. This graph from 0 to 3 is a parabola opening downward. And the nice thing about a parabola, as opposed to maybe like a fourth-degree polynomial or a cubic that looks just like this on part of its function, is that a parabola has an axis of symmetry that runs right through its vertex. So this part here and this part here are exactly symmetrical. So if I rotated it around 4, which would be right here, what would the shape be? It would be another bundt cake. And because we're 1 unit away from the axis, just like we were right here from 0 to -1, and because of the symmetry of the parabola, you should get a bundt cake that is, in this case, exactly the same. Okay? Now let's see what the setup would be. I'm glad you brought this to our attention. If I did that, let's see what would change in our equation. We'll just adapt this one, and then we'll go to the calculator for confirmation. The 2 pi in the front would stay the same, right? Because we're still slicing it vertically. We're still slicing it from 0 to 3 because that's where the region was. Is the height of the slice still top minus bottom? Yes. The only thing that's going to change is the radius. Okay, so let's get rid of the 1 plus x. And if you want to come over here, now your axis is over here at 4, and the distance now from the axis to one of those slices would be what? Well, let's see. Here's how you would configure it. If this is 0 and this is 4, then the distance between the y-axis and 4 is a constant, right? It's 4. The distance from the y-axis to the slice is x, always. So if the whole thing's 4 and this piece is x, what we're interested in finding is what's left over, right? Which would be what? It would be the total distance 4 minus whatever x is, right? 4 minus x. That ends up being the radius, 4 minus x. Now, here's how you can do it in the future. If you don't want to draw it out, remember I told you the region itself can be represented by x, and it's always right minus left. Your axis in this case is at 4, which is to the right of the region. So if you do right minus left, you're doing 4 minus x, which is 4 minus x, right? Let's go ahead and drop that in here, 4 minus x. And even though it's going to give me a different equation, because of the symmetry, I should get the same value, right? Let's see if the calculator knows that. If I just hit second enter, that'll recall the previous line. And then if I scroll back over to my radius, plus 4 minus x. Same number of character spaces, so there's no inserting. Ready? Hit enter. Look at that. Isn't that cool? It worked. Yeah. Now, what if you change the axis of rotation from 4 to like 5? Would that be the same? No, because now your axis is 2 units away. You're going to have a bigger hole, right? The hole is going to be bigger. But should the volume of the cake be the same? Or should it be bigger? It should be bigger because you're taking an area and you're sweeping it through more space. And when you sweep an area through more space, you generate more volume. So maybe this would be the bundt cake you would use if you were having a bigger party, right? More friends coming over. Maybe 2 instead of just the 1, right? Math parties. Plenty of cake for everybody. All 3 of us. Yeah. Thank you, Marissa, for bringing that to our attention. I had written that in there on purpose so we could look at that, but, you know, sometimes I just get too darn excited. All right. So there you go. That's the shell method, and we actually looked at the 2 parts where the axis was not the y-axis, and it's right minus left. Okay, so back to what I already said. You decide how you want to slice it. You then compare it to the axis of rotation, and now there's a method that will accommodate that, unless it explicitly or specifically tells you otherwise. So here we go on example 9. Find the volume of the solid formed by revolving the region bounded by those graphs about the y-axis. Okay, so it's a volume of solid revolution. Step 1 is to identify the region. And we'll just assume it's a no calculator up until the end. Maybe if we're curious, we'll calculate it on the calculator. X squared plus 1, that's a parabola up here. Opens up. And I'm not going to give it a distinctive name yet. Y equals 0, also known as the x-axis. X equals 0, also known as the y-axis. And x equals 1, also known as El Toro. I don't know. Just made that up. Okay. There's the region. And, of course, finding the area would be a piece of cake, right? But we're after the volume. We're rotating that around the who axis? The y-axis. All right, the y-axis. So that's going to generate, if you want to kind of, this is kind of easy to generate because it's already over there. It's going to generate something that looks like that. Again, it'll resemble what appears to be perhaps a shot glass, maybe. Right? Perfectly cylindrical on the outside. Got this nice parabolic bowl on the inside to accept, the shots of Kool-Aid that you would be adding to your soda water. Yeah. How do you want to slice the region? I would prefer to slice it vertically. Yeah, indeed. For a couple of reasons. The first reason I'm going to at least look at a vertical slice is that my equations are already given to me solved for y in terms of x. But secondly, I can then use just a single setup for my height because it's going to be the parabola minus the x-axis all the way from left to right. If you were to slice it horizontally, it would require two setups, yes? Because it would be vertical line minus vertical line up into the vertex, and that'd be vertical line minus the parabola. Okay, let's go for it. Are we ready? Vertical slice, vertical axis, two vertical lines are related how? Parallel to each other. So the volume is, parashell has how many pi's out front? 2. Can't just buy one pi shell, got to get 2. Parashell. From x equals 0 to 1. Radius times height times dx. Nothing squared. What's the radius? We'll do that one first. Well, it's the distance from the axis to any one of those slices. Yeah, it's just x, right? When your axis of rotation is just the y-axis, then the distance off of it is just the x value. And, of course, our x values are going to range from 0 to 1. So it's just x. The height is top minus bottom. That's x squared plus 1 minus 0. Or just x squared plus 1. So there's your setup. We'll go ahead and evaluate this one. It's easy enough. If you distribute, you get x cubed plus x dx, and 2 pi then goes for the ride, 1/4 x to the 4th plus 1/2 x squared from 0 to 1. And we get 1/4 plus 1/2 minus 0. 1/4 plus 1/2 is 3/4. So we got 2 pi times 3/4. And that ends up being 3 pi halves. 3 pi halves the radian angle at 270 degrees? No. 3 pi halves cubic units, which I think is about a jigger. Good. You ought to know what that is. Good. That's good. That's another shot glass reference, and I'm glad you didn't acknowledge that. Oh, okay. You have better sensibility than I do. Right. Here I am talking about shot glasses on a recording, and y'all are like, no. That's right. I want to come back and learn tomorrow. All right. I'm just saying it looked like one, right? Yeah. Okay. Bartending's a good career, though, by the way. Yeah, you can make quite a bit of money. Yeah. Good way to pay your way through college as you're taking calculus classes and stuff. Anyway, you want to see what it looks like if we do the slices horizontally? Let's see. Did you do it that way? Let's do that. Let's do it. Let's do it horizontally. I want to point something out here. When you slice it horizontally, notice that from 0 to 1, which is where the vertex is, the horizontal slice is going to be right minus left, and it's not going to be a variable at all, right? It's a constant. In fact, if you were to rotate that thing around, you would have just a what? An actual cylinder, right? So if you wanted to slice it horizontally, here's what you could do. The volume is, what is the formula for the volume of a right circular cylinder? Pi r squared h, right? What would the radius be from 0 to 1? 1, right? And what would the height be from 0 to 1? 1. So you could actually do the bottom portion by using a geometric formula rather than using calculus. But you could certainly use calculus also as well. Now for the top part, we are going to have to use calculus. because we have dy and it's right minus left. So this right here, if x squared plus 1 equals y, then x is going to equal the positive square root of y minus 1. And of course, we take the positive version because we're in quadrant 1. So then that's going to be the sum of the slices with the 2 pi out front. Oh, I'm sorry. What's it going to be? My bad. If the axis is vertical and we're slicing it horizontally, that's going to be the what method? The washer method. Cowabunga. Big R and little r. All the more reason why we don't want to necessarily do this. But we'll set it up. We got pi, sum of the infinite slices now from y equals 1 up to y equals here. What's the y value on the parabola when x is 1? 2 of beefy bracket big R squared minus little r squared. And then big R is going to be 1 minus 0, or just 1. And then little r is going to be the square root of y minus 1 minus 0, or just the square root of y minus 1 squared, which ends up being just y minus 1 dy. Now, I'm not going to evaluate it, but if you did, guess what you'd get? 3 pi halves. Yeah, y'all could verify that over spring break. Okay? It's good to see it from the other perspective. You know, the more we reinforce both methods, you get more comfortable with each of them. All right. So far, so good? Both methods work there. But the parashell was a little bit easier, a little bit faster. Okay. There's one last type of volume that we're going to find in this section. And it's a volume of a solid that is not formed by revolving a region around an axis. Okay? It's a volume of a solid for which we still know the area of the face of the cross-section, but we're going to be building these by stacking known geometric shapes onto slabs. All right, so let me show you what that looks like. I have some models over here that have been around since before Mr. Cook's time. That tells you how old they are. And they're kind of in a state of dilapidation. But I think they will do a fair job of illustrating the concept. If I could bring them over here. Let's see, one more. I got it. Thanks. Yeah, got it. Now, as I went back here to gather my models, I realized that I have something else that I brought from home that'll help you with the shell method. So, not that you need any more clarification on the shell method, but we're clearing out my son's room the other day, and you know, he's a freshman now, but this was one of his favorite toys when he was a little dude. And you know, it's got the fire truck, you know, Fisher Price, I believe. They're great. You know, it's got a little ladder. So let's say you're trying to find the volume of this fire truck. And by volume, I don't mean the decibel level of its siren. Woo-woo. The volume. Well, you could take the volume of the, whoa, and then look, there's a little yellow school bus under there, right? Little school bus. And it's got, it's a cool school bus, man. Look at this. It's got a, oh, is that what it is? I thought it was like a sunroof. Yeah, it's got, well, I can't even open it because I don't have fingernails. But anyway, you take that off, and look, there's a little police dude under there, right? Little police guy, and he's got like a little simulated light there for little kids, you know. And then you take him off, and then you got the little speeder dude on the bottom. And unfortunately, he's the last guy. But there they are. And those are like nested Russian dolls, right? So those would be like the shell method. You have the outer shell, which is the fire truck, and then the next inner shell would be the school bus, and then there you go. The shell method. You find the volume of each of those vehicles, and then you add them all up. And these, by the way, this is the beauty of Fisher Price. You could stack them. And notice when they stack, read the numbers from top to bottom. 1, 2, 3, 4. Really helps with your counting. Anyway, there's the shell method. And I know you can't see this on the video, so just Google Fisher Price nested shell method calculus toys. All right, see what comes up. All right, so anyway, what we're going to be doing in this next section is we're going to be using the same idea, which is this. The volume of a solid is going to equal the sum of the infinite slices from A to B, in this case it would be from left to right, of the area formula of the face times dx, which would be the thickness of the face. Now, the only difference is in this type of problem, we are going to be building like a slab. Okay, I was in construction before I was a teacher, and we never poured a slab like this, ever. But let's assume that we have a slab that looks like that. Okay? Now we have the magical powers to fly and suspend ourselves above it so that we are now looking straight down upon this slab. This slab, if you want to put like coordinate plane on here, might look something like this, so that we actually have two functions. And what we're going to do then is these are going to be like prefab buildings. We are like opening up a subdivision, and we poured a bunch of slabs in the subdivision that look like that, just a bunch of them. Like we had some kind of ready-mix form template, and we just poured a slab, 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 slab. And we're trying to sell out the subdivision. Well, the customers, when they come in, they don't have a choice on the slab, okay? Which means they don't have a choice of the square footage of their house. They're going to have to use that slab. But what they do have choices of is the aesthetic appearance of their house, the structural integrity of their house, and the volume of their house, the spaciousness of the house. Because what we're going to do is we are going to stack perpendicular to the x-axis. And this will be said, okay, these are the restrictions. We're going to basically slice it vertically. We're going to stack shapes on there for which we know the area of the face, okay? And the easiest thing to build on there would be to stack a bunch of squares. All right, so let's say I have this slab right here, and this homeowner came in and they wanted to stack squares straight across from left to right on that slab. This would give you an idea of what their house might look like, okay? Now, these are finite slices, so the thickness, when you stare down from above, what you're seeing, I have it kind of outlined in black there. You see what you're seeing? You're seeing this right here. That's the span from across. But because it's a square, that ends up being the width along the base of the slab, which when you look at it face on the elevation side, it ends up being the height as well, right? So when you look at it, the cross sections are squares. Do we know what the area of a square is? How do you find the area of a square? Side squared, right? And the thickness of each slice is dx. Now that's going to be a pretty cool looking house, right? Because the width, as it goes to basically 0 in the corners, that house is going to go back down to a height of 0. And if you can imagine this being like sliced thinner, you're not actually going to see this graduated step. It's just going to be this nice, smooth looking roof. It's going to look pretty cool. Maybe kind of like some kind of cool helmet. I don't know. But anyway, this is the idea behind it. If I can come up with an equation for that, which I'm not going to call h of x here, I'm going to call it s of x for side length. Because the geometric formulas that we're going to use typically have side lengths in their dimensions, length times width times height. We're just going to call it s for side length. Remember, we're staring down from above. If I can find the equation for that, then I'm good to go. Because here's what it would be if I used squares. Let's say I was using squares. What I'm staring at from above is this right here. And the thickness of that slice is dx. And provided I can find the area of the face, I'll have it. Well, that's going to be s of x on the bottom and s of x on the side. So the area as a function of x is just going to be s of x times s of x, or s squared of x. Would you all agree? So the volume is going to be then the sum of the infinitely thin slices from A to B, right here, from A to B, of the area of the cross-sectional face, which is the square, so it's s squared of x, times the thickness of each slice, which is dx. So let's go ahead and put some numbers to this, all right? Example 10. says find the volume of the solids whose bases are bounded by the graphs of y equals x plus 1 and y equals x squared minus 1 with the cross sections taken perpendicular to the x-axis. That kind of phrasing right there is the red flag that tips you off that this is a solid. You're finding volume, but it's not generated by revolving around any axis. It'll say cross sections, and this is one of the few times where it'll specify how you're slicing it. It'll tell you slice it perpendicular to the x-axis or perpendicular to the y-axis. Okay, so step one, we need to identify the region. We're identifying now the slab on which we're going to be building. And of course, x plus 1, we know what that looks like. It has a y-intercept of 1 and a slope of 1, so it looks like that. And then x squared minus 1 has a y-intercept of negative 1, and it opens up like that. So the region again, and this is the same one that I just drew above, but this one's a little bit more exact. It's in the right spot. That's the slab on which we're building. And because it said we're going to be taking cross sections perpendicular to the x-axis, that means a vertical slice. So this right here, if you want to draw it, means dx, which means now everything has to have x in it. We're going to be slicing from left to right, and we have to write our cross-sectional areas in terms of x. So let's do something. Let's find, first of all, the points of intersection, okay? Because notice they do define their own interval of integration. POI, x plus 1 equals x squared minus 1. And we would have to do this if we were just finding the area of that region, or if we were taking that region and rotating it around some axis. We would still need the points of intersection. So I'm going to get everything on the right-hand side, and I get x squared minus x, and that becomes minus 2. So you get x minus 2, x plus 1 equals 0, and we get the x-intercepts to be, or the points of intersection to be x equals 2, and x equals negative 1. All right, so there's negative 1, and there's 2. We got our points of intersection. The next thing that we can do is we could actually figure out what the equation is for s of x. You could just go top minus bottom each and every time, but we're going to use many, many different shapes. So I want to go ahead and figure out what that is one time and then just recall it. So the side length, which is what we called the height in the area section, is just the top curve minus the bottom curve. And the curve that's on top is x plus 1 minus the curve that's on the bottom is x squared minus 1.
Teachers, please turn your TVs to channel 4 for the morning announcements, or you can view them on your iPads at vhstv.com.
All right, so if I simplify by distributing, I get negative x squared plus x plus 2. There is my side length. And I know now that if I plug in any value of x into here from negative 1 to 2, it's going to give me a positive number. Okay? Now, let's proceed to part A. I am going to be stacking squares in there. So that first couple that comes into the subdivision and they want to build on that slab, as I already showed you, they're going to be building the house with the square cross section. Okay? So, here we go. The volume should be the sum of the infinitely thin slices from left to right, which is going to be from negative 1 to 2, of my side length squared. That's the area of a square with respect to x. That's your setup. Now, because we've already defined what s of x is, if this were a free response, you would get 2 checks for that. Now, I'm going to do this entirely on the calculator instead of doing it by hand. So let's go ahead and do the following. If you wanted to, instead of call it s of x, if you wanted to actually type in your 2 equations like as y1 and y2, you could do that as well. And then when you type it in, you would just do like y1 minus y2, whatever you prefer. I'm going to go ahead and just type in s of x as one equation. And I'm going to get negative x squared plus x plus 2. because we're going to be using that same side length each and every time. So it'll save some keystrokes. You don't have to do top minus bottom. So I have that in Y1. And now if I go to my home screen, here we go. To figure out what the volume of that house is, it's math 9. Is there a pi out front? Why is there no pi out front? Because my cross-section is not circular. Yeah. Both the shell and the disc and washer method, remember, had circles involved. So that was where the pi came from. This is just -1 to 2. And then for my function, yeah, just a negative. That won't work, will it? For my function now, here's the benefit again of putting it into Y1. You don't have to worry about like parentheses and then square it. You could just say alpha trace, number 1, and then square it like that with respect to x. Just like that. And you get 8.1. Now that represents 8.1 cubic units. Okay? 8.1 cubic units. And you wouldn't have to write cubic units. But that would be the volume of that house. That would be how much air conditioning space they would have to maintain, right? Or heating space. They have a certain square footage, but each of these houses are going to have different volumes. Okay? Now, the next people come into the subdivision, and they have to have the same slab. That's all we got, guys. But we do have different shapes laying around, and so these people want to be different from their neighbors. So these guys come in, and they're like, okay, you know what? I like the boxy look of the neighbors, but you know what? I'm a big fan of flat roofs. You know why? Not because I necessarily like leaky roofs, you know, because water sometimes can accumulate on a flat surface. I'll put a lot of tar and stuff on there, but I like flat roofs because you get kind of an outdoor living space, right? You can live on the roof. In fact, you could call it the party deck. This is the party deck right here. So the neighbors have the party deck. So here's what their house looks like. Now, notice that the base is a rectangle. So when you stare at it straight on, that S of x is going to be one of the dimensions, but the height is a constant, right? And it's a height of 2. Now, the advantage to this is when they have to vacuum in the corner, it's a little bit easier for them to do that, right? The other house went down to nothing in the corner, so they're like this in the corner. These folks can just walk right up to the corner because it's the same height all the way through. Now, hopefully the height is tall enough so that they can walk around standing upright in their house. Okay? Maybe it's like not 2 feet, but maybe it's like, I don't know, 24 feet, whatever. We don't know what the units are. But here we go. Let's see what we're looking at from above. When I'm looking at it from above, what is this brown thing representing? It's representing, bless you. I'm staring down at this. Okay, this is S of x. And the height is 2, and of course the thickness is dx. So what is the formula now for the area of the face of that rectangle? 2 S of x. Very good. Because one of them is 2, that's one of the units. So the volume should be the sum of the infinitely thin slices from -1 to 2 of 2 S of x dx. There you go. That's the party deck's volume. They have the same exact square footage on the floor as their neighbors, but really double it if you call the party deck living space. Yes, you could bring the 2 out, and I'll go ahead and do that. 2, math 9, you don't necessarily have to do that, from -1 to 2, this time just S of x, alpha trace, enter. No squaring, because the 2 is one of the dimensions, dx, enter. And you get 9. 9 cubic units. So it turns out that they actually have the same square footage, but slightly more space inside, which means if they keep it cool with the AC, they have a bigger AC bill. But maybe they spend all their time outdoors on the roof on the party deck anyway. Who knows? Okay, Now, the next people come into the subdivision. They're like, really? That's the only slab you have? Oh, you're going to give me a great deal? Okay, all right. You know what? They look at the neighbor and they're like, we're not party animals, but you know what? We really dig the rectangle thing. And so they combine what the first people and the second people did. They like the variable height of the first people in the subdivision, okay? And they never vacuum in the corners anyway, so that's not a problem. But they also like the rectangular look. They don't like it looking so symmetrical from left to right. So here's what they're going to do. They're going to stack rectangles on there so that the height, the roof, is 5 times bigger than the base. They like big vaulted ceilings, okay? Now, I don't have that one to show you, but you can imagine the square house with just a roof that comes up much higher. Wherever the base is, you go up 5 times, not just 1 time, okay? So let's see, what we're staring at from above then would be something like this. This is S of X right here. That's what we're staring at from above. And then this would be what? 5S of X, and of course the thickness is dx. So what would the area of the face be? 5 S of X times S of X, which is 5 S of X squared. Perfect. And that looks like, yeah, X. That's a 5 times S of X. So the volume would be the sum of the infinitely thin slices from -1 to 2 of 5 times S of X squared dx. Now here's what's cool. This is getting into what we're going to be finishing up with tomorrow. The 5 is a constant multiple. We can pull it out front. So it's 5 times the integral from -1 to 2 of S squared of X. Have we already seen the integral from -1 to 2 of S squared of X? That was the square people's house, which remember from part A was 8.1. Yeah. So the answer is going to be 5 times 8.1, which would be 40.5. Big time electric bill. All right. Same square footage, a lot more volume. Now here's what it's going to come down to. Everything that we're going to be working with except for the party deck house. They're the exceptions, right? Where the height was specified to be a constant. Most of the other shapes, in fact, all the ones that we're going to look at, they are going to be some magic constant multiple times the square man's house, times side squared. And so it's going to come down to memorizing what the magical coefficient's going to be, and then it's just the integral from left to right of side squared. Okay? And for a rectangle whose height is n times the base, the magical coefficient is n. In this case, it was 5. Okay, very good. We'll pick up there tomorrow. We should finish tomorrow. So we're looking like the worksheet's going to be due the Tuesday we get back from spring break. Okay? The Tuesday we get back from spring break.